17.5, divergence and curl. So we'll find the curl of a vector field, the divergence of a vector field, and apply theorems about related to the curl and divergence. All right. Okay, so let's go back and review the nabla operator. Right? I mean, the operator, this upside down triangle, it's just a hollow operator. It doesn't mean anything if you don't have a function to act on. For instance, this partial derivative with respect x. I mean, you're taking the partial derivative with respect x, but the question is of what, right? We need a function to act or an expression to act on it, all right? So, well, we already learned this operator. You might remember from the gradient. You know, when we take nabla of f, well, this nabla operator is acting on a scalar function to produce a vector valued function called the gradient. Well, which we have already gotten deep into what the gradient is. All right. So it's a conservative vector field. That means it's a vector field whose potential functions, the scale, blah blah, all that. You guys already know what it is about. But well, so the gradient it's only one of the differential operators on vector calculus. There's two more. Not the other two is the divergence, while the other one is the curl. Okay, so the divergence of a vector field. So the divergence acts on it's the nabla operator acting on a vector value function, not on a scalar like the gradient. Right? So what does that produce? So that's essentially the dot product between the nabla operator and the components of the force field that it's given. So there's a little typo. There's two equal signs, and it actually should be here. All right. So, this is a little weird because while for the gradient, the nabla operator acts on a scalar function to produce a vector, for the divergence, the nabla operator acts on a vector to produce a scalar. So, in this case, if you take the dot product between partial with respect x, partial with respect y, and partial with respect z. So dotted with the components m, n, and p of a vector field, take the partial of m with respect x plus the partial of n with respect y plus the partial of p with respect z, which is what we have here. That looks a lot like a scalar. Do you see vector notation there? No, it's not a vector, it's a scalar. Alright, but I mean, yes, we were going to take a bunch of partial derivatives, but in the end, what does that mean? What does the divergence mean? Well, so again, keep in mind that a force field, a vector field, which is a field full of arrows representing a streamline, what else? An electrical field or a magnetic field, or the current of water or of air, well, what does that mean? So depending on the nature of this vector field or this force field, the divergence measure expansion or contraction of a vector field at each point right here. So, and here's the thing, if the divergence equals to 0 at all points of the region, then we say that the vector field is source free at that region, because you can think of infinitely many points on these vector fields, right? On these fields. So depending on the direction of these vectors given by the vector field, you could have a sink, you could have a source, or actually at that point there's no it's source free. There's nothing coming out, nothing coming in. Think about the radial field in space. You see how all these vectors are going out of the origin? Well, so that means there's an expansion. So if we compute the divergence of the radial field, that's going to give us, a positive result, all right? Now, here's the thing. Think about the other picture right here to the right. Well, we have a vector field x squared y where we have different vector fields. So, for instance, at this point, 1, 1, do you see this vector coming out? So that means it's behaving like a source. While, for instance, a vector right here. So do you see this? Yes, we see this little vector, this tiny vector going out like a source. I agree, but think about the vector pushing the point in here. That looks a lot like compression because look at the length of the vector. All right, look at the length of the vector. So the compression vector is stronger than the expansion vector, right? So at some point we may have, like in this case, for all values of x, we're going to have a compression for all values greater than negative a half. We're going to have expansion, all right? See the direction of the vectors. Okay, let's have a look at one example to compute the divergence. Okay. One example is more than enough. We're going to need to do 17 examples about divergence. Okay, so find the divergence at the point 2, 1, negative 1 for the vector field given by f equals all that madness here. All right? Okay, how do we calculate the divergence? So the divergence div f, that equals the partial of m with respect x plus the partial of n with respect y plus the partial of p with respect z. All right, so and again, this is m, this is n, and this is p. All right, partial of the component m with respect x. Okay, is that 3 x squared y squared z plus the partial of the component n with respect y. Well, do you see there's no y's? 0 plus the partial of the p component with respect z. Do you see there's no z's? 0, right? So the divergence, the point, well, the divergence of f will be simply these terms: 3x squared, y squared, z. All right? Well, so that's the expression to calculate the amount of, to calculate the divergence, which again, it's a rate of change of compression and expansion. That's what it means. That's what it means. So those of you who are going to take physics, I believe it's physics 2 or physics 3, which of the two actually covers hydraulics? Is that the second or the third one?
Hydraulics, the second one, probably like one chapter.
Okay, so I think it's both of them, right? I think it's the end of the second and the beginning of the third one, right? There's like an overlap, right? So, all right. So you will look a lot of this fluid mechanics. Yeah, fluid, not hydraulics, fluid mechanics, right? Fluid mechanics, like Pascal's principle, the flow of a flux, of a fluid. I mean, a lot of pretty cool stuff. All right. Well, so now we're going to evaluate the divergence using this expression for any single point, and actually notice they're polynomials and no restrictions. So let's see about it. Let's find the divergence of f at the point 2, 1, negative 1. That is 3 times 2 squared times 1 squared times negative 1. Okay, so 2 squared, that's 4 times 3, that equals to 12 times 1 squared, which is 1 times negative 1, is that negative 12? Okay, it's negative. Great, but what does that mean anyway? We don't want to just compute crunch symbols and numbers. I mean, we do a lot of that, but I mean, what's the real meaning? This means we have compression. We have compression or a sink. So depending on the point of view, compression of an object or of a fluid, or having a sink or a source at the point 2, 1, negative 1. If it were positive, we would have had expansion or a source. If we had done a 0, it's source free, or the fluid in question is uncompressible. That's what it means. All right, it's uncompressible. That's also the part you're going to get into in physics, But the thing you're learning those tools in this class. So that's why you should take at least the whole calculus trilogy before getting into physics. But the prerequisite is what? Calc 1, right? To 50. No. Take all the math before taking physics. Okay. Curl, number 3, curl. The curl of a vector field, okay, again, this operator will act on a vector field in a similar way that divergence did. The gradient acts on a scalar to produce a vector. What's it called? The divergence acts on a vector to produce a scalar. However, the curl acts on a vector to produce another vector. Oh, we will see a lot of pretty cool connections here. You'll see. All right. So the curl of a vector given by the components n and p that are functions of x, y. Oh, no. Yeah, it could be x, y or x, y. And see, again, if you have a vector in two dimensions, you would need to add a third component of 0 because this involves a cross product. And again, the cross product is not defined for vectors in two dimensions, but the trick is to put a 0 in the third component, okay? And you may need to do this. Anyway, so it's given by, okay, the first row of the matrix, it's the notation ij, okay, the standard unit vectors. The second row is the nabla operator, that is the partial derivative operators. And what else? In the third row, it's the components of the vector field. I mean, look at all these. Yes, and you can do it, right? You can calculate. You can follow the instruction of following partial phi with respect blah 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 blah. But again, what does that mean? And that's the most important part. If we don't discuss what it means. Okay, so the curl. It's a force that causes rotation. That's all it is. But I mean, look at this vector. Why do we have an I component, a j component, and a k component? Well, the first component here describes the rotation about the x-axis, while the second component describes the rotation about the y-axis, while the k component describes the rotation about the z-axis. All right? So that's what it means. That's what it means. All right? Notice that the curl is a vector, not a scalar. So if the curl of f is 0, what do you think it means? There's no rotation at all, right? Also, there's a little typo there. What do you think the typo is in there? What's the typo here?
Plus sign?
Which one? No, not the plus sign. There's a little typo here. And no, I didn't do it. I didn't do it on purpose. I just realized there's the typo I haven't fixed in years, all right? That 0 right here represents the 0 scalar, and while the curl is a vector, I need to express this 0 as a bold K0 or put an arrow at the top, all right? Yeah, that's the typo here. I mean, let's have a look at this picture right here. So here it is. I mean, what we already described about the components of the curl. Rotation about the x-axis, rotation about the y-axis, and rotation about the z-axis, right? That's what it means, right? That's what it means. Okay, so let's have a look at one example, all right? So we're given a vector field f. So find the curl and determine if the vector field is irrotational. Now, is F a conservative vector field? We will see about it because, like I said, we're going to see some pretty cool connections with what we had seen in previous sections. Okay, so, all right, let's go for it. M, N, and P. All right, so we want to calculate the curl of F, which is nabla operator cross with f. Okay, so this will be the determinant of the matrix ijk and the operator partial with respect x, partial with respect to y, partial with respect z. And these are the components: 2xy, x squared plus z squared, and 2yz. And I mean, you guys know how to evaluate a 3 by 3 determinant, right? I mean, you can use the definition, which is using the expansion by cofactors, which is the more formal way to evaluate a 3 by 3. Or you can use the Cyrus's rule I showed you at the beginning of the semester, but I mean, that's more like a shortcut. That's more like ghetto math, if you will. But I mean, if it works, it works. That's fine. Go for it. However, I'm not going to do any of those two. I'm not going to do any of those two. Actually, I'm going to use the formula from before, but I'm not going to write all this Jacobian notation for partial derivatives. I'm going to use the subscript version instead. All right? So let me write that form at the top of the page. That means, so curl, that is p with respect y minus n with respect z in the direction of I minus p with respect x minus m with respect z in the direction of j plus n with respect x minus m with respect y. I'm pretty sure that if you look at these partial derivative terms, something is coming to your mind. But I mean, don't worry. I'm not expecting that you see it at first glance. We will conclude about it. All right? Okay. So, partial of p with respect y, isn't that 2z? All right? Minus partial of n with respect, what's that? Z old? No. Yeah, with respect z. Partial p with respect y to z. Partial of uh, n with respect z. That'll be 2z. Minus partial of p with respect x. Okay, isn't that 0? Minus partial of m with respect z. That's also 0. J plus, finally, partial of n with respect x. That's 2x. Minus partial of m with respect, what's that? Y. That's also 2x. K. Right? What's the result here? 0. Hey, 0? The 0 vector. Again, the curl acts on a vector to produce another vector, alright? Yes, so 0, 0, 0. Okay. Let's talk about this result. So, is F irrotational? Yes, because it's also, there's no rotation about the exam. I mean, there is, but it's 0, right? So there is rotation in all directions. So that might be an expanding or contracting vector. I don't know. Now, here is the thing. There's something I would like you to see. We got zeros for this, right? Okay. How about we equate components of vectors? Remember the fact that two vectors are equal if their components are equal from week 1? Okay, check this out. This guy equal to that guy. This guy equal to that guy. And lastly, this guy equal to that guy. All right? Okay, so p sub y equals n. Oh, no. P sub y minus n sub z equals 0. P sub x minus m sub z. I'm ignoring the negative sign. All right? I mean, you can put it, but divide both sides by the negative. The right hand side, it's still going to be 0. All right? And lastly, n of x minus m sub y equals to 0. If I move the negative terms to the right hand side with positive sign, n sub x equals to m sub a. Does that remind you of anything? What's that?
Is conservative.
What is that?
It's conservative.
So, but I mean, it's conservative, but what are these equations?
It's not like the divergence.
Not the divergence, but yeah, it has to do with conservative, yes, and it's right here. Aren't those the conditions to check that a vector field is conservative? So here is another way to check that a vector field is conservative by finding the curl of it. If the curl is equal to 0, there's no rotation. That means it's conservative, and that means if you want to evaluate a line integral, whatever the trajectory, it's going to give you the same result. If you're evaluating a line integral over a closed curve, it's going to give you 0 and a bunch of meaningful things. Isn't that cool? Isn't that a cool connection? Vector operators with line integrals is crazy. This is crazy. All right? Yes. A vector field in space is conservative if and only if it is irrotational. That is, the curl of f equals 0. That's a great result. That's a great result. All right? Okay. Find the curl of the vector field given by this madness here. All right? So, which is m, n, and p. All right? Okay. Find the curl. Curl of f, that means p sub y minus n sub z in the direction of I, minus p of sub x minus n sub m sub c in the direction of j, plus n sub x minus m sub y in the direction of k. Alright? Let's compute partial derivatives here. Alright. So, p with respect y, that is 3y squared, z squared, minus n with respect z, that is 1, just 1, in the direction of I. Okay, so just by computing the first component, is this vector field conservative? No. Is it rotational? No, it's going to cause rotation, right? Because it's not 0. Okay, let's compute the other two. Minus p with respect x, that is 0, minus m with respect z. Okay, that's 4xy squared z cubed in the direction of j, plus n with respect x, that is 4xy minus m, that is m with respect y, that is 2x y z to the fourth in the direction of k. So no, it's not conservative. Right? Not conservative. Alright, that means if we were to evaluate a line integral that for which the driving force is this vector field into moving a particle from point A to B, we would need to know what that function c along the particle has to travel. Alright? Because it's not conservative, it's not independent of the path, it depends on the path we follow to go from point A to B. Because if we parameterize different curves from point A to point B, for sure we're going to get different results because it's not conservative. Otherwise, conservative, you know the whole story. All right. Wait, that's about it, right? Oh, theorems related to divergence and curl. You know what? I'm going to skip that, and actually I'm going to remember that quiz I gave you with the blank integrals? Expect another one.